Okay, good afternoon, everyone. Can you all hear me okay? Great. I cannot see a single thing now that light's been turned on. That's quite insane. Okay, welcome to my talk this afternoon on protecting encryption keys with Microsoft's Azure Key Vault. So my name's Stephen Haunts. I've had quite an interesting career working for many different companies in lots of different verticals. But these days I'm now independent, so I do a lot of in-person training, writing books, as well as teaching for Pluralsight, and I also do some consulting for a blockchain consultancy in the UK called Block3. But I spend most of my time going around training people these days. So today, this is loosely what we're going to look at. We're going to talk about the threat of data breaches. We're going to do a little, very quick high-level cryptography overview. Then we're going to talk about different key management options that are in place these days. And then we're going to talk in a bit more detail about Azure Key Vault. And then I'm going to show you some different patterns and practices you can use when using Key Vault or hardware security modules. And we'll be doing some code demos for that. So hopefully the Wi-Fi gods are going to be kind to me this afternoon. Okay. So first of all, let's talk about the threat of data breaches. Now, I've got a website here. It's a company called Breach Level Index, and I quite enjoy showing this because they have some really good stats on their homepage. So as you can see here, since 2013, and I believe these are US-based statistics, there's been 9.7 billion records stolen or compromised to date. Now, that number doesn't really surprise me or shock me. You know, we hear about data breaches pretty much every day in the news. The bit that does shock me is the line that's underneath it that says only 4% of those data breaches were secure breaches. And what it means by that is the data was encrypted, so even though the data was stolen, it was practically useless to anyone who got hold of it. So that's quite a low number, so we want to get that number a lot higher, which is why I spend a lot of time talking about cryptography in .NET specifically and helping people with Azure Key Vault. But it's also, you know, the stats are broken down at the bottom of the page there. So I mean, 9.7 billion is a large number, so that equates to about 5 million records every day, 210,000 every hour, 3,500 every minute, or about 58 records a second are being stolen. So that's quite a shocking set of numbers. So what about the effects of data breaches? So as an organisation, there's some quite bad consequences that can come from data breaches. So it can lead to a lot of reputational damage, which can then come to a lot of loss of sales as people go elsewhere. You lose your customers. And also you can get legal action from your customers and other companies, as well as very high compliance costs, especially if you work around card payments with PCI DSS or any of the other regulatory bodies. And it could also potentially compromise the safety of your customers. So as an organisation, the threats are quite bad. And there's a high certainty of financial stipulation against you. But also, as an individual, as a private citizen, there's some quite bad consequences as well. So we're having our personal data stolen, names, addresses, phone numbers, quite personal details about us. This can lead to identity theft and impersonation, which can then, in turn, lead to a loss of a loss of money through financial theft. But the sad thing is, data breaches are inevitable, so we need to kind of change our mindset. We're never going to get away from the idea of data breaches. We just need to try and protect ourselves better and hope we can get the criminals to move on somewhere else. So it's not a case of if you're going to get breached, it's more a case of when you get breached. And I think that's a good kind of mindset to prepare yourself when you're building your software solutions. Now, it's very easy just to focus on perimeter security. You might say, I've got really high-tech intrusion detection systems, I've got firewalls, so my company must be good. And it is good to do that sort of thing. I'm not saying don't do that. But what if you've got threats from within your company? What if you've got some rogue people in operations who have access to your production databases? I mean, what are you going to do about those people? Because typically, a lot of data, especially in databases, might be encrypted at rest, and that's a good thing. So SQL Server on Azure encrypts at rest. I think Cosmos DB does as well. But if you've got someone in your company who has access to those systems, what's to stop them from just, select starring out of all your tables, copying that data into a spreadsheet, and then walking off with it? So what we need to do is we need to start looking at other ways that we can protect our data by being a bit more specific with row level or record level encryption. This is even more relevant today now that we've got things like GDPR in full force. So if you get caught up in a data breach, the fines for GDPR can be quite high against your organisation. So part of the regulations on GDPR is about the safe storage of data. So that's what the main theme of today is giving that extra level of safe storage to your data in your organisation. And I've worked for many different companies. I've taken the company names off because this is being filmed, but I've worked for various different internet banks in the UK, and the typical sort of data protection and encryption work that we'd do there would be things like a secure PIN number storage and secure PIN viewers for the websites. Doing typical hashing or salted hashing of passwords. This is something that a lot of people are very familiar with these days. And integrating with hardware security modules. I've also done things in retail finance where we're dealing with a lot of customers' debit cards. So that's involved the safe storage and handling of customers' card numbers. These are very typical things you might have to do if you work in retail or retail finance, as well as HSM or hardware security module integration. I've also done a lot of work around insurance claims management as well. So, similar sort of theme. We've got lots of passwords being stored. Typical things like record level, multi-tenant record level encryption, as well as integration with Azure Key Vault. But I've also done a lot of work in healthcare as well, where we've had to safely encrypt patient records. Because obviously, if data gets stolen about patients and then you've got a history of their illnesses and the drugs have been prescribed, that can be very embarrassing because it's very, very personal data. Now, a lot of these companies that I've worked for, and probably very similar to what people in the room work for, all have one thing in common, in that they're all regulated or regulatory environments. So in the UK, where I'm from, we have something called the FCA, the Financial Conduct Authority. So they govern a lot of our financial and insurance companies. But then you've got PCI DSS, which I'm sure a lot of people are familiar with, which is all around the legislation around card safety, payment card safety, and around health in the NHS. So really, storing people's personal data in this day and age is quite a high-stakes game. But not just for large companies. I mean, even for small startups. Now we have things like GDPR, which kind of sets in stone, the expectations of what we do with customer data. It really is a high-stakes game. If we get it wrong, then the consequences can be quite bad for our companies. So as software developers, we have quite a lot of control over making sure that we're not caught short. So before we look at Azure Key Vault more specifically, I just want to do a very quick primer of a few crypto things, like the 4 pillars of cryptography. So we have confidentiality, integrity, authentication, and non-repudiation. So these are kind of like the 4 core pillars of cryptography or modern cryptography. Now in .NET and a lot of other languages, we typically solve them using these primitives. So we have AES and RSA, which are 2 encryption algorithms, one's symmetric, one's asymmetric. For integrity, we have things like SHA-256 or SHA-1, MD5, SHA-3. There's lots of different algorithms we can use for integrity. For authentication, we have things like hash message authentication codes, which can be based on different hashing algorithms like SHA-256, but the key difference is when you hash your data, you actually provide an encryption key. So the person who wants to create a hash, your recipient wants to create the same hash, they need to be in possession of that key. And then we have non-repudiation, which is something we solve with digital signatures. So non-repudiation is all about not being able to deny that a contract has been signed, for example. So if one of you signs a contract with me that says I will pay you $5,000 for completing some work, and we sign that and have it witnessed, you can't then turn around later on and say, no, actually, it was $8,000 you're supposed to pay me. And I go, well, no, it's not. We've got a contract, so you can't repute what was in the document. So that's kind of what non-repudiation and digital signatures help us with. Now, typically, we can use all of these different primitives together to do what's called hybrid encryption, and we're going to touch on a few of these concepts today when we look at some of the demos. So for encryption, it's broadly broken down into 2 areas. So we have symmetric encryption and asymmetric encryption. Symmetric, we typically use algorithms like AES, DES, or triple DES. But if you're building a new system, you really want to go straight to AES. Now, this works by having a single key. You use that same key for both encryption and decryption. Asymmetric cryptography is slightly different, so we might use things like RSA. And this works with a split key pair. So the keys are mathematically linked, but you have a private key and a public key. So your private key, you keep secret, that's yours. You never let anyone else have it. But your public key, you can give to anyone else. So if someone wants to encrypt some data and send it to you, they request your public key, encrypt it with that public key, send you the data, and then you use your private key to decrypt that data. Now, there's pros and cons to both of these different types of algorithms. So things like AES, symmetric encryption algorithms, they're fast, they're very algorithmic in the way they work. They get data, split it down into blocks, and perform very algorithmic operations, which is what computers are very good at. But the problem is, those encryption keys are very hard to share between different people. So if I'm using AES and I want to give my key to one of you, how do I do it? Do I give it to you on a USB stick? Probably not a great idea. Do I want to email it to you? Terrible idea. Do you want to stick it on a server? Again, not a very good idea. So getting that key from point A to point B is very difficult. Whereas things like RSA, on the other hand, the RSA algorithms are actually very slow. It's all based around modulus arithmetic, and it's things that are harder for computers to do. So therefore, it's a lot slower, so you've got a performance penalty. But it does make the key sharing problem easier, because as we said, you have the split key pair. One you keep secret, one you can give to anyone. So it actually makes the key sharing aspect slightly easier. Now, in .NET, just show of hands, if I can see, is everyone .NET developers in here? Okay, pretty much most of you, that's cool. So in .NET, you'd use things like AES Crypto Service Provider for doing AES encryption, and you might use RSA Crypto Service Provider for doing RSA encryption. So that's a very, very high-level primer of some of the things that we're going to be looking at later. So let's now look at key management options. So there's various different ways in which you can store keys, and probably the worst way is doing this, which is flat files on a file system. Now, it seems laughable to include a slide doing that, but I've worked for 2 companies where when I've gone onto some of their servers, there's a folder on D drive called keys, and then 2 XML files sitting in there, which are their master RSA encryption keys, which is quite shocking. But you don't want to do that because if anyone breaks into that server, they've got your keys. That's very bad. So the one that we're most familiar with is certificates, things like X509 certificates, Kerberos, etc. And these are a very well-known, proven, well-tested way of installing keys on systems. They help you provide the identity of who it's been issued to or where it's been issued from. They allow you to do public key verification. You can install them directly onto servers, and they're very robust and proven, which is great. Now, some of the benefits are that generally there's minimal involvement for the end user. So if you're installing an enterprise system, your end users don't have to get involved with how the keys are installed. You can generally automate it these days. You don't really need any additional hardware. They're very easy to manage, and they're pretty much supported by every system out there, whether it's a Mac, Windows servers, Linux servers. They're very well supported. But there's a level we can go that's better than that, which is to use something called a hardware security module. Now, a hardware security module is a 1 or 2U rack-mounted device which you'll put in a data center. Typically, you might buy 2 and have them in different data centers so you can synchronize between the 2. Now, a hardware security module is designed to be completely tamper-proof. So if you try and hack into it or if you try and remove the case, then it will detect this and it will wipe itself and you have to send it back to the manufacturer. And it does this with things like, pressure sensors, heat sensors, light sensors. They'll cover the chips all in like a hard resin so you can't get into the chips. So they're designed to be secure. And we typically use these to store, very important master keys or certificates. But there's a problem with hardware security modules in that typically for most companies, or a lot of smaller companies, they are very cost prohibitive. I mean, these things can cost anywhere from like $50,000 and up. So for small companies, it really isn't something that you could use. But we have an alternative option, and that's to use Azure Key Vault. So Azure Key Vault is an abstraction over a series of hardware security modules that Microsoft provides us, and it allows us to safeguard our keys, secrets, and certificates. Now, Azure uses this hardware. This is the Thalys Enshield hardware security module. I expect it's quite expensive. I went onto their website to try and get a price, and it wanted me to phone them to have a conversation. So to me, that says expensive, because they're not telling you the price up front. But Microsoft, thankfully for us, have gone out and bought lots of them and installed them all over their data centers around the world. Now, there's 2 ways in which Azure Key Vault can work. There's kind of 2 primary modes. We have software and hardware. Now, regardless of which mode you use, your master keys are always stored on the HSM hardware, so they're always hardware protected. But in the software version, any encryption and decryption operations you do, they'll be done on compute VMs inside Azure, but they'll use those protected keys. But the hardware version, all your encryption and decryption options will actually happen on the hardware itself. Now, as you can imagine, there's a cost difference between the 2. So a typical recommendation is that for your development and test environments, you'd use the software version, because it's going to be a lot cheaper for you. But then for your production environment, which is where you really need the best hardware you can get, that's when you'll use the hardware version of Azure Key Vault. Programmatically, there's absolutely no difference between the 2. Once you set them up, there's no code differences, which is great. So let's have a quick look at some of the costs, just to give you an idea of what this might cost you. And some of the techniques I'm going to show you later will help you get that cost down to virtually 0. So for non-key operations, so for non-encryption operations, you're looking at between two different tiers. You've got standard and premium pricing tiers. So you're looking at about 3 cents per 10,000 operations. So it's not that expensive, really. Certificate operations, if you want to do a certificate renewal request, that's going to cost you $4. And then using that certificate is 3 cents or 3 US cents per 10,000 operations. Now, for the software encryption option, if you're using RSA 2048, which is the standard encryption key size on Azure Key Vault, again, across both pricing tiers, you're looking at about 3 cents per 10,000 operations. So again, it's quite cost effective. Now, they have got higher strength RSA keys in preview at the moment, which is currently free if you're using the software version, but there will be a cost associated to those when they come out. Now, if you're using the hardware version of the HSM, then you can't use the standard pricing tier. You have to use the premium tier. So for the standard default size key of 2048 bits, you're looking at about $1 per key, and then again 3 cents per 10,000 operations. The higher strength keys, it's a tiered pricing model, so your first 250 keys will cost you $5 per key, and then the price staggers to get lower the more you use. So that's just to give you a kind of a rough impression of what the price is. Whereas if you sort of go and buy one of these devices, you could be looking, $50,000, $60,000 or higher. Now, one key thing to remember is that once you put a key into Key Vault, it never comes out again. So you never get to see the raw key, ever. Now, you can go into the Azure portal and back up the key, but the backup you get will be a fully encrypted version of the key. So you can never actually see the original key, and that's deliberate. Now, unfortunately, in the time we've got, we actually can't go through the full setup process because we haven't got enough time to do that. But the documentation provided by Microsoft is actually very good. They've done a really good job of the documentation for this. So link on the screen there, or if you just go to Google and type Azure Key Vault Getting Started, and that will run you through the process. It's not that complicated. But broadly, what you're looking at, if you're using PowerShell to set this up, is you create a resource group or reuse an existing resource group. You create the Key Vault, you specify the resource group, the region you want it set up in, and whether you want the hardware or software variants. And then from there, in the portal, you can actually create keys, upload secrets, etc. Once that's done, you have full blade access to it in the portal, like you would with any other asset in Azure. So you can administer it, monitor it from there. Now, if you want to programmatically access the Key Vault, you've got a few extra steps you need to do. And first of all, you need to go into Azure Active Directory and register your application. And then that will give you your application ID and shared secret that you need to present. I know whenever you mention AzureAD, it normally fills people full of dread, but actually the process is actually fairly straightforward. Now, there's kind of two things that we're going to be looking at storing on the Key Vault today. So first of all, we've got keys. So they're RSA encryption keys. And then the other thing is secrets. Now, secrets are effectively just small pieces of text that you can store in the Key Vault, and then the Key Vault will actually handle the encryption of those for you. So that could be things like database connection strings, app IDs or API keys for other systems that you're using. So anything that you don't necessarily want to check into GitHub or TFS, you can store in Azure Key Vault. And it's effectively a key value pair store. Now, the source code we're going to be looking at today is all available here on GitHub. I've released it under MIT license. You can just take it, use it, remix it, do what you want with it. So if you're looking to get up and running with Key Vault quickly, just take what's in there if you want. Now, the thing you have to do when you set it up is you install the Microsoft.azure.keyvault NuGet package, and that gives you everything you need. It's .NET Standard 1.6 compliant, so it works with .NET Core, hence why I'm presenting on a Mac. But it works across Windows, Linux, and everything else that .NET Core or .NET Framework currently runs on. So let's look at an Azure Key Vault Hello World, and let's hope the Wi-Fi gods are going to be kind to me this afternoon. So I've got a Key Vault already prepared, and I've got a simple project here called Simple Encrypt and Decrypt. This is going to be our Hello World of Azure Key Vault. So what I've done is I've created an interface, and I've just abstracted out the operations that we're actually going to use for the Key Vault, just to make things a bit more readable. And then from there, I've created a Key Vault class. I've just hacked in the client secret there and the Key Vault address. But then I've implemented, things like create key, which literally just calls down to the Azure class library provided by Microsoft. And then there's a base class there which just handles things like setting up the JSON web keys. So all this will happen behind the scenes for you. As I say, feel free to take it and use it yourself. So let's look at the code. So first of all, I'm going to initialize a key vault. Then I'm going to create a key called Stephen Haunce's key. I'm then going to encrypt a piece of data. So we've got hello world, because it wouldn't be computer science without hello world. I'm going to encrypt it, then decrypt it, display the text, and then I'm going to clear up after myself and delete the key. So let's hope the Wi-Fi works today. So I'm creating the key. And once we've done that, we get a URI returned to us. It's a bit difficult to see, but that's a URI, which is effectively the ID you're going to use for that key. So whenever you want to encrypt anything, you give it that ID to say, I want you to use this key set. So we have our string. Now I'm going to do the encrypt operation. So I turn that string into a byte array. I'll just come down here, call one method on the client library, and then that data is sent back as a byte array. So that's our encrypted data. Then if I want to go and decrypt it straight away, again, I'll just call the decrypt method on the client library, and that's going to return a byte array with our decrypted data. So if I convert those both to strings, a bit hard to see there, so you have to use your imagination. There's a lot of gobbledygook in that variable there, which is our encrypted data. And then you can see where we've decrypted it straight away, so it says hello world. So we've taken a piece of data, we've encrypted it, and we've decrypted it straight away. So we've tested that Azure Key Vault's working for us this afternoon. And I'm just going to delete my key, because I like to keep things tidy. Okay. Right, back to the slides. Now, in my time using Key Vault, there's been various patterns and practices that me and my teams that I've worked with before have sort of recognised. So I want to present some of those to you this afternoon. And we've got 6 patterns that we're going to explore. So multiple environments, configuration of secrets, local key wrapping, key versioning, password protection, and digital sign-in. So first of all, we'll talk about multiple environments. And the key thing I want to stress here is that if you're creating a key vault, never use the same key vault between your test environments and your production environments. So the key vault you use for production, you need to treat as one of the most important assets in your organization. So you never want to share the same one between test and dev. Now, what you could do is you could have one key vault that you use for all of your test environments. That's absolutely fine. I've seen people do that before. And then have a separate one for production. Or if you like to script your environments and you do infrastructure as code, then you might as well go and create a new key vault per environment. But the important thing is never share keys from your production environment to any of your other environments, because that's just a generally very bad idea. Okay, so the next one is configuration as secrets. So we've mentioned before that you can store secrets on the key vault, and secrets are blobs of text up to 25K in size. And it's kind of like a key value pair store. So you give it an identifier and the text, and you just tell the key vault to store it for you. You don't even have to provide encryption keys. It's all managed behind the scenes by Key Vault. So typical things you might use these for are connection strings. The connection strings for your databases or Cosmos DB. You may as well store them in here so no one else can read them. API keys, Redis cache connection strings, or just generally anything that's confidential that you don't want any other developer or anyone to basically have access to. Now, the secrets are versioned in Key Vault, so if you have a secret called My Secret and you write it twice, then you'll get 2 versions in the Key Vault, and then you can refer to them by version number if you want to. So there is a versioning ability there if you so need it. So let's look at how to do that in code. And the good thing is everything we're showing today is actually very simple to do, which is good because it actually removes the barrier to entry if you want to incorporate any of these. So what I'm going to do here is I'm going to create a secret called Stephen Haunce's secret. My secret is Mary had a little lamb. I'm going to store that into the Key Vault, and I'm going to retrieve it straight away. So we should be able to receive the same piece of text back. So let's just quickly validate that works. Okay, so I've called set secret. And again, I get a URI back for that secret, which we can store if we need it. But then if I say get secret, but pass in my original sort of ID, which I provided, I can then retrieve that secret. So you can see we've received the text back, Mary had a little lamb. So we now know that that works, so that's good. And it's just a few lines of code to do that. And the next pattern is local key wrapping, and this is where things can get quite interesting and quite powerful for us. Now, doing an encryption operation on Azure Key Vault or hardware security module is generally quite slow, so there's network latency, and it's generally quite a slow operation. So you don't want to be doing thousands of them all in one go because it is a slow operation. So we want to use a hybrid solution. So generally what that will look like is if you want to do all our encryption locally using AES, because it's fast and flexible and we can do it client-side, but the key that we use with AES, we want to protect that in the HSM. So what we're going to do is we're going to encrypt it using one of the keys on the HSM, and then we can store that encrypted key just in our database. If it gets compromised and stolen, then we know that that key has been protected by a more powerful RSA key in the Azure Key Vault. Now the good thing about this is if you're careful with how you do this. Say you have a session going into a web API, you might recover and decrypt your AES session key at the beginning, and then you might do, hundreds of encryption or decryption operations. But really, all you're being charged for is that one time that you recover the AES key. All the other encryption operations that you do locally aren't going to cost you anything financially. So this is a really good way of keeping your costs down on Azure. So let's take a look at how that works. So in this project file, so I've got a few other helpers. So I've got a method for generating a random number. This is how we're going to create our AES key. We do that using RNG Crypto Service Provider. It's effectively a cryptographically secure random number generator. We pass in a length, which will be 32 for 32 bytes or 256 bits. And then we just tell it to fill the array full of random data. So that's how we're going to generate our encryption keys for AES. Then I also have a file here called AES Encryption, and that literally does a standard AES encryption operation in .NET using AES Crypto Service Provider. So we have the encrypt operation and the decrypt operation. Quite straightforward in how they work. So if we're looking at encryption, we pass in a byte array of our data that we want to encrypt. We pass in a key, which is 32 bytes. But we also have this thing called an initialization vector, which is 16 bytes of entropy that you pass into AES, which kind of helps it kickstart the encryption process. You need to store that initialization vector, but it's not a secret key. It's just something you need to store. So let's look at what this looks like. So again, we're going to create a key in the Key Vault. Then I'm going to generate a local key. So this will be a 32-byte key I'm going to use with AES. I encrypt that key using the Key Vault, so I've now protected it. So now if we imagine that we go and save that key off in a database somewhere. Now we come back in, maybe through a web API or something, and we want to do some encryption using that key. So the first thing we need to do is to decrypt it with the Key Vault. So we can't use that key until we've decrypted it. We generate our initialization vector, which again is just a random number that's 16 bytes in length. And then we do an encrypt and decrypt using AES. This is happening client side. There's no calls out to the Key Vault at that point. This is all happening locally. And then we can view that encrypted text. So let's run it. So I'm going to create my key. So I've created my local key, which is 32 bytes in length. I'm now protecting that with Azure Key Vault. So what we have in this byte array here is completely encrypted. So you can convert that to a base 64 string, store it in your database. So now we want to do an encryption operation. So first of all, we have to recover that key. So I'm going to decrypt it using the Key Vault. Then I'm going to create my initialization vector. Now I've got some data I want to encrypt. So I've got a string here that says mega top secret stuff. We're going to encrypt that. So we come into our AES operation, encrypt it, pull back the byte array with our encrypted data in, and that's now encrypted. So now just to prove this works, I'm going to decrypt it straight away, convert those to text. So if we look in the encrypted text folder variable, we can see we have our encrypted data. Might be a bit hard to read on the screen, but it is there. And then in decrypted data, we have the string mega top secret stuff. So the key thing about what we've done there then, I mean, this is a very simple example, but we've used the key vault once to recover the key, and then we could go off and do, 1,000, 10,000 encryption operations if we wanted to. But we're only being charged for that one time that we recover the key. Now, if you're in a very high transaction volume company, that could make quite a big saving for you. Okay. So an example where I've used this, and it's quite an interesting usage pattern, so I'll tell you about it today. I worked for one company where we were doing an online claims management system for insurance companies. So we were a software as a service provider, and it was a platform that was all hosted in Azure, and we could onboard different insurance companies, and then when they log into it, or their customers log into it, they act as different tenants, so they get their own branding, their own colour schemes and styling. So it looks like their own system, even though it's our SaaS product on the back end. Now, we have logically, one deployed application, and we could have, hundreds of insurance companies all using it. Now, each of those insurance companies, when we onboard them, they'll get their own master keys set up in Azure Key Vault for them. So if we had 10 insurance companies, we'd set up 10 keys, one per insurance company. Then what we'd do is, using that key wrapping technique that we just looked at, we'd use AES to do individual record level encryption of all the personal information for their customers. But that encryption key that we used with AES was protected by their master key in the key vaults. So what this meant is that even though all the insurance company's data was stored together in one big database, or set of databases, we actually had partitioning via encryption key in the data. So insurance company A would have all their PII data encrypted with their key, insurance company B would have their private information protected with their key. So if any of those tables ever got stolen and leaked, we'll be quite confident that we could class that as a secure data breach, because they can't identify any people because it's all encrypted. So essentially it looked a bit like this. So we had the claims platform in the blue box there. Each insurer had their own set of keys in the key vaults. And then somewhere we'd have like a mapping table in our system. So we'd have a tenant ID, which is the ID that uniquely identifies that insurance company. We'd have the key ID, which was the URI to the key in the key vault. And then we'd have an encrypted AES session key that would sit in a database. So if we wanted to do an operation on insurance company one's customer data, we'd first have to look at their tenant ID, find their key ID, bring the key down, send that AES encrypted key to Key Vault to be decrypted with their key, and then we could do local encryption, decryption of their data. So I thought it was an interesting use case, and it's something that is quite common, especially for SaaS systems these days where you have multiple tenants. So as you said, the advantages are the local encryption operations are faster. You decrypt the key on the HSM, store it in memory, so that reduces network hops and latency. And that actually makes it easy to rotate keys as well. Because if you imagine that you've got a security officer at your company, and they may say that you have to change your master encryption keys every 6 months, for example. Now, if you was using that encryption key in Azure to encrypt, say, 1 million records in your database, when you go and change that encryption key, what have you got to do? You've got to go and re-encrypt all of that data. But using this key wrapping system that we've used here, the only thing you'd have to re-encrypt when you change that key is that local AES session key. So you don't have to go and re-encrypt all of your data, because the AES key is still the same. You're just encrypting it with a new master key. So actually it makes doing key rotation very easy. Okay, so the next sort of pattern is the idea around key versioning. Now, the idea of changing keys is a bit like how you might change the locks on your house. So if you have a potential break-in, or someone tries to break into your house, the first thing you're going to do is probably change the keys, change the locks. So this is kind of like the digital equivalent of changing locks. Now, I think we just looked at now, so we might have key version 1.0, and we use that to encrypt our keys. But then if we rotate the key, we end up with key version 1.1, and we then re-encrypt that local key. So that's kind of what we've just talked about a moment ago. But also, because of the key versioning attributes in Azure Key Vault, it means if you write or if you tell it to create a new key with the same ID, it'll actually create a second version of the key in memory for you, so it will maintain a history of the keys if you want it to. Now, an area where I've used this before is we worked at one company and we built what's called a PCI DSS card token vault. Now, what this is a system that runs on a separate network, and we had a system in there which is designed to protect and encrypt credit card numbers. Now, the way we had this system, and we worked with a PCI auditor to help build this, is that we had a rule in there. So say for every 1,000 cards that you encrypt, we generate a new key. So looking at the diagram there, we've got a bunch of operations which are done using key version 1. We then add a new key, key version 1.2, and then all subsequent cards that are entered into the system were done with key 1.1. And we'd keep on incrementing the key that way. So it's just another way in which you can think of using the key vault. Okay, so the Key Vault can actually help us with some password protection ideas as well. Now, generally, when we authenticate users on our systems, we use passwords. Now, we all know as professionals that passwords aren't very good, but they're not really going to go anywhere because it is still one of the easiest ways for our employees and sort of families to access their machines. So let's look through, a different scale of ways of dealing with passwords from worst to best. So obviously the first one is plain text passwords. That's something you don't want to do. That's very bad. Hence the shocked face on the screen there. So the next one on from that is to do hash passwords. Now this is where you literally get the password. You might create, say, a SHA-256 hash of that password, then you store it in the database. So does anyone do that at the moment? A couple of hands. So it's been something that's been done for a long time, but it is susceptible to some problems. So you can do a brute force attack against those passwords, or you could do what's called a rainbow or dictionary table attack. And this is where you have huge multi-gigabyte dictionaries of pretty much every password combination you can think of, and the subsequent hashes. So using tools like Hashcat, which you can download for free off the internet, and a lot of these password dictionary files, which you can also download for free, actually makes it quite easy to recover passwords. As a good example, if you ever try to demo this to anyone, there's a website here called crackstation.net. So what you do here in the grey box, someone's pasted a password. You type in the captcha, hit crack password. It's worked out that it's a SHA-256 hash and that the password is secret69. So this is quite a good website that you can use to demo to people how bad general hash passwords are. So the next best one on from that is to do what's called a salted hash of a password. Does anyone do that currently? I can see a few hands up. So this is kind of like the next step that you can do. And the salt is effectively a large random number that you might generate using that random number generator we played with before. You append it onto your password, and then you hash the password. And then you store the password and that salt in your database. Now, you could also use a HMAC as well. A hash message authentication code is another way of doing it. So you pass in the password you want to hash, and then the key that you pass into that HMAC is actually the salt. So that's another technique you can use. Now, again, this is better than doing standard hashing of passwords, but what it doesn't help us with is the fact that we're seeing such rapid advancement in graphics processors on computers that people are using GPUs and tools like Hashcat to try and crack passwords. Now, you may have a salted hash password that's perfectly secure now, but who knows what graphics cards and GPUs will be like in 5 years' time. You just can't predict it. So what we want to do is we want to look at another way of hashing passwords where we algorithmically slow down the whole encryption process. And we do that by using what's called a password-based key derivation function, which is what we use in .NET, or something like bcrypt. Now, bcrypt isn't supported in .NET. There's open source implementations, but password-based key derivation functions are. And they're very simple in how they work. So we have a password, which we pass in. We have a salt, which we pass in, just like before. But then we have another parameter called number of iterations. So if you pass in 10, it's going to repeatedly hash that password 10 times. If you pass in 50,000, it will do it 50,000 times. And the reason we do this is we're trying to slow down the encryption process. So if a GPU and a tool like Hashcat can, say, test, 5 billion password combinations a second, you can probably slow that down so they can only try, say, 100 passwords a second. So it just makes it infinitely more complex than to crack those passwords. Now, to do this in .NET is very straightforward. There's a class called RFC2898 derived bytes. It's not the most obvious of classes, but the way it works is very simple. So you just instantiate it, give it your password as a byte array, the salt, number of iterations, and then you call get bytes. Now, in this instance, we're returning 20 bytes. That's because this particular function under the covers uses SHA-1. Now, SHA-1 only returns 160 bytes as a hash function, as a hash code, which is 20 bytes in length. Now, the number of iterations, as we said, affects the speed of the hashing process. So we've got an example on the screen here. 100 iterations might take 2 milliseconds. 100,000 iterations might take nearly 1.5 seconds, or 500,000 might take nearly 7 seconds. Now, as an application designer or an architect, you need to work out what's an acceptable weight to impose on your users. So some systems, you might log in and you might notice there's like a couple of second delay. It's probably because they're doing this or a bcrypt operation behind the covers. So you'd think we're good. That's kind of one of the best ways of storing passwords currently. Does anyone use password-based key derivation functions? On there, a few there, or bcrypt or anything like that? A few people. So that's a really good way of doing it. But using Azure Key Vault, there's another little trick we can do, which just gives us that extra little chink of protection. So this is the process we've just looked at with a password-based key derivation function. So say we're hashing our password and we're doing it 1,000 iterations, for example. But then what we could do is we could perform one extra hash afterwards, or a HMAC, where we pass in a key which has been protected using the Azure Key Vault. Now what this means is that if anyone ever wants to generate that same hash code, they have to be able to recover that key using the Key Vault. So if anyone steals your password table, the hackers have first got to, try and work out what that key is to recover the HMAC, and then once they've done that, they then need to try and break the iterated hash. Now, even if they do manage to somehow guess the HMAC key, which is nigh and impossible, all they're going to see is a load of gibberish anyways, and they're not going to see a meaningful password. So this actually makes it really robust. So let's take a look at that in action. Oops. So in our demo project here, I've got a few more helpers. So we've got one here called HMAC, and that just does a standard HMAC operation in .NET, just a few lines of code. So we instantiate the HMAC SHA-256 class. We give it a key, which is a byte array. We'll use 32 bytes in our case. Give it the data you want to be hashed, call compute hash, and you get your hash code back as a byte array. So that's quite straightforward. The password-based key derivation function, as we've already seen, is very easy to use. Again, it's just a few lines of code. So we can use that helper as well. So if we now go to our example code. So first of all, I'm going to create a new key in the Key Vault. I'm then going to generate a local key, just like we did before with the key wrapping. So this is just 32 bytes of random data. And then I'm going to encrypt that key with a Key Vault. Again, same as what we looked at before. So we could then go and store that key in our database to recover later. So now we want to hash a password. So we come back in, we decrypt the key using the Key Vault. We create a password. So we've got a password here, we love Troy Hunt. We create a salt, which is 32 bytes. We then hash it using our password-based key derivation function. So I'm using 20,000 iterations here. That's a local operation. There's no Key Vault involved there. Once we've done that, we then create the HMAC of it using that decrypted key from the Key Vault. So let's run that. So I'm going to create my key. Gives us the key ID back. Create our random number, 32 bytes. I'm now going to encrypt that with Key Vault. So what we have stored in here is our key encrypted with RSA using the key on the Key Vault. We can convert it to a base 64 string, put it into a database at that point. So now let's assume someone's come back and they want to hash a password using our system. So first of all, we have to recover that key, and we do that with the Key Vault. So we decrypt the key. We have our password. We generate our salt. We then go and run the iterated hash. So I've got a byte array of our password there. We've got the salt. We've got the number of rounds or iterations, which is 20,000 in our case. And we hash the password. So now we've done that, typically that's where a lot of people might stop and then just store the results of that hash in the database. But we're now going to create a HMAC. So we pass in that already hashed password and the key, which we've already recovered from the key vault. And we then hash it. So if we display those on the screen, I don't know how easy that is to read, but the top one, you've got the original hash password. So that was done with the password-based key derivation function. It's 20 bytes in length, hence it's a shorter hash. But now, an interesting property, now that we've created that separate HMAC of the password afterwards, we actually get a much longer hash off the back of it. So actually, it's a much more secure hash and it is longer and harder to brute force, especially as they need to recover that key first. So for the people that might try and steal our password table, this is actually really bad for them. So they can't even begin to start trying to break through the password-based key derivation function until they've first managed to recover the hash of that HMAC, which they can't do because the key is encrypted with Key Vault. So if you're using the default key size in Azure Key Vault, that's 2048 bits of RSA key, that's going to give them a very, very hard time. Now, because we're using Key Vault, obviously making a call to Key Vault is not the most instant operation. There is an area of latency on there. So as an application designer, you need to work out where you're going to use this. Would you use it for all of your standard users on your system? You may feel that, yes, you want to, or you may think, well, actually, this might only be worth using for administrators or super users on our systems. It's kind of up to you where you decide to use it, but it does give you that kind of extra bit of security. So the final pattern I want to look at then is using the Key Vault to do digital signatures. So as we said, in our 4 pillars of cryptography, digital signatures they satisfy the non-repudiation pillar of cryptography. So this is where we can use it to effectively try and sign contracts. So has anyone used a service like DocuSign before? Only a handful of people. So DocuSign's a good analogy for this. So it's a system where you can upload a PDF of a contract. Maybe it's a job contract or you're buying a house. You go on there, you do like a fake weird electronic signature, but then it creates a digital signature behind the scenes. So if ever you want to dispute what's on that contract and take it to court, which has happened many times, you can't disprove what's in that contract because you've already signed it and it's been electronically signed. So this is the same principle. So a digital signature is a mathematical technique used to validate the authenticity and integrity of a message, software, or digital document. Now, when we create digital signatures, there's 3 sort of main operations that we need. So first of all is key generation. We've already seen how to do that. We've done that in pretty much every demo we've looked at this afternoon. You need a signing algorithm, and you need a verification algorithm, both of which are provided by Azure Key Vault by default. Now, the way it works is when you want to create a digital signature of a piece of data, because it's using RSA behind the scenes, there's a limit to how much you can actually pass into the digital signature in one go. So you can't pass in more than the length of the key. So typically what you do is you'd have your document, it could be a PDF. You create a hash of that document first, so you get like a smaller hash back, like a 32-byte hash, and you then create a digital signature of that hash. So if we look at this picture here, so we've got the guy Bob at the top there. He wants to create a digital signature. Now he uses his private key to create that signature. There's a key difference there. So when you encrypt with RSA, you encrypt with your recipient's public key, then they decrypt with their private key. When you do digital signatures, it's the other way around. So you as the originator are using your private key to create the signature. Then if the recipient wants to validate that signature, they do that with your public key. So that's how they know that that document came from you, because you're the only person in possession of that private key. Now, normally, if you're doing this in .NET with our Azure Key Vault, these are the 2 classes that you'd want to use. So we've got RSA PKCS1 signature formatter and RSA PKCS1 signature deformatter. Brilliant pieces of API naming there. But those are the 2 classes we typically use. But using Azure Key Vault, it does digital signatures by default for us. So we don't need to use those classes. So let's have a look at that. So this is our last demo. Okay, so the only additional helper method I've got in this project is a standard SHA-256 hash. That's the only additional bit of code we need. So, like before, we're going to create a new key, because each of these demos creates the keys and deletes them at the end, just to keep them self-contained. So we create the key. Now we have a document that we want to create a signature for. In this case, it's a string, but you could be loading up a file. So we have a string there. Then what I do is I create a standard SHA-256 hash of that string. And then once I've got that hash, I've called it document digest here, I then call the sign operation on the key vault. I tell it what key we're using. That's the key ID that was returned here. I give it the hash of that document, and it creates a signature. Then if I want to verify it, I just call verify. I give it the key ID, the original hash, and the signature we just created, and it will return true or false. True, we trust that signature. False, we don't, so we want to discard it. So let's run that. So create the key, create our document, create a hash of the document, create our digital signature. Then we verify it straight away. Now it should say true here because we've literally just created the signature. So that's come back as true. So now let's run it again. Creating a new key. Take a hash of our document and create the signature. Now when we send the signature to our recipient, we're going to send the original document, we're going to send the hash that we generated, and we're going to send the signature. So there are three things that we send to our recipient. So now let's pretend that we're, some dodgy hacker. We've intercepted the message as it's gone. We've changed the document, which means the hash will change. So let's just, change this hash so it's invalid. Now, if we call verify, that hash isn't going to match the signature, or the signature's not going to match that hash, so we should get false back, which we can. I don't know if you can read that on there, but take my word for it, it says false. So that's how easy it is to do digital signatures in Azure Key Vault. It literally is just a few lines of code. So, as I said before, it really does lower the barrier to entry for using a lot of these things. Oh, there's PowerPoint. There we go. Okay, so those are the 6 patterns that I wanted to talk about, and they give us quite a lot of flexibility. So let's just summarize what we've looked at today. So we started off by saying that, data breaches are getting worse, they're not getting any better. But the sheer number, doesn't really surprise me anymore. It's going to happen, it's going to carry on happening. But the bit that was worrying is the fact that it says on there only 4% of data breaches were secure. So we want to get that number higher. And as software developers, I think we're in the best place to try and do that. So data breaches are inevitable. You want to go with the mindset that it's not if you're going to get breached, it's when you're going to get breached. If you go in thinking that it's going to happen, you can start protecting yourself better from it. So our favourite technique, and obviously the reason why we're here in this talk, is to talk about Azure Key Vault. So this lets us safeguard keys, secrets, and certificates. It uses certified hardware security modules based on the Phallus Enshield hardware. So Microsoft has gone to the effort of buying all of that hardware for us, and we're just effectively leasing it for not a lot of money. Now, as I said before, it's very easy to set up. We didn't have a chance to go into the setup because we only have an hour today, but the documentation is very, very good. So if you want to have a play around with this and you've got an Azure subscription, just run through the instructions there and it will get you up and running. Now, the main patterns that we looked at today, so we talked about the idea of multiple environments. So you don't want to share your production Azure Key Vault with your test environments, just the same as you wouldn't want to expose you shouldn't be exposing data from your production databases in your test environments. So you want to create separate instances of the software-based Azure Key Vault for dev and test and UAT. We looked at the fact that you can store secrets in Key Vault, so just think of it as a key value store database where the values are encrypted using master keys in the Key Vault. So great for configuration strings, connection strings, passwords, API keys, or anything that's classed as confidential in your system. So then we looked at local key wrapping. So this is one of the techniques where we can really lower the cost, the actual financial cost of using Azure. And this was all about using the Key Vault to protect AES keys, but then using those AES keys, we can do local encryption operations where we're not actually calling out to the Key Vault. So that really, gives us the benefit, the speed and flexibility of AES, but then we have the benefit of using RSA on a protected Key Vault to protect those keys. Then we looked at the idea of key versioning. So if you do want to make use of multiple versions of the same key, you can do so. You just write the key with the same name twice and you get a new version, and you can access all those previous versions. Then we looked at the ideas that you can actually use a Key Vault to help you with password protection. So we looked at password-based key derivation functions. And we then looked at how you can actually do an authenticated hash of that hashed password using a key that's protected by the Key Vault. Something you might want to use for like administrator or super user accounts in your software. But it really gives you a good extra level of protection on your passwords. And then we ended up by looking at digital signatures and how we can use the Key Vault to, with just a few lines of code, create digital signatures and verify signatures for us. So, as I mentioned before, all of that code that we've looked at is available on GitHub there. Feel free to take it and use it. It's under the MIT license, so you can do what you want with it, but if it breaks, it's not my fault. But if you do want to experiment with this will get you up and running really, really quickly, and then you can refactor the code and do what you want with it. Does anyone here have access to Pluralsight? Cool, quite a few people. So I've got some courses that might help. So if you're interested in more of doing, understanding what you can do with cryptography in .NET, I've done a fairly in-depth course, about 4 hours long, called Practical Cryptography in .NET. This really takes you on a deep dive of what all the individual primitives are in .NET and how to use them all together. Then I've got another course, which you can see in the background there, called Enterprise Data Encryption with Azure Revealed. This is kind of like a high-level introduction to Key Vault. So it doesn't go into as much depth as what we've covered today, but it covers some of the topics we talked about. And then if anyone's interested in how blockchains work, I've also got a course called Blockchain Principles and Practices, where by the end of the course, you will actually build a basic blockchain implementation in C#, so using crypto primitives in .NET. So it's a good, fun kind of computer science level type course, but it's really useful because when you're sitting in a boardroom with CEOs and they say, I want a blockchain, if you watch that course, you'd actually understand what one is because you would have built one. Final plug, I promise. I write a lot of books. I've written a lot of books in the Gentle Introduction series that are all available on Amazon, so they're there as paperbacks and Kindle. And that's it. Thank you very much for coming along this afternoon. It's a really good turnout, so thank you. I'm around for the rest of the conference. Is anyone going to PubConf tomorrow night at the party?
Yeah, of course.
Yeah, so PubConf is absolutely fantastic. I'm one of the speakers, so I apologise for that now. So we get to do a 5-minute really silly talk whilst we've had a lot of beer. It's always good fun, so come along to that and support us in that. That'd be great. Thank you. Oh, if you could all remember to vote on the way out as well. Green means you're awesome, and the amber and red cards don't really mean anything, so just put the green one in. Thank you.